Okay, so I've been asked to give a presentation on the star TPC, so this is really an introduction to the star TPC. There are a lot of things that one can talk about with the TPC, so there's no way that this can cover every topic, and I would certainly be fine with opening up to questions at the end to discuss things that may not be in the presentation, but I also wouldn't mind an interruption if somebody feels like I haven't explained something sufficiently in the middle of the presentation. So I'd rather we have questions and people understand rather than I say too many things and we don't understand everything that goes through. So start out with talking a little bit about really what the TPC measures. And I think people don't always fully understand exactly what it is that the TPC measures, and understanding what it measures helps to understand some of the performance of the TPC. So I've listed here on this second slide quite a few different possible things that the TPC could be measured, or that people think it might measure about the particles that come out of our collisions. And you can see it's quite a list. A lot of people think maybe the TPC measures the charge of particles, maybe it measures the momentum of particles. I think momentum is a big one that a lot of people think that what the TPC, what you get out of the TPC is the momentum, or maybe more specifically the rigidity, which is the momentum over the charge. TPC also could measure the path of a particle as trajectory, the species of particles, protons, pions, kaons, ionization of the gas in the TPC, energy loss, and then these things we call dN, dx, or dE, dx. So there's a lot of things that people might think that the TPC measures. On slide 3, I've tried to list what it is that the TPC really does measure. And in fact, by itself, the TPC does not measure the charge of a particle. It does not measure the momentum of a particle, or the rigidity of a particle, or an energy of a particle. What the TPC does measure are space points of the path of a particle through it, and that is its trajectory. And if we combine that trajectory with information that we know about the magnetic field that the particle is going through, then that can help us figure out what the rigidity or momentum is. The direction of the trajectory and knowing the magnetic field can help you determine the sign of the electrical charge of the particle. But again, the TPC by itself does not measure these things. It's a combination of the TPC measuring the trajectory along with knowledge about the magnetic field. The other big part of what the TPC does is it measures the ionization in terms of the number of electrons liberated, and sometimes we call this dN. So the number of electrons liberated over some segment of path in the TPC. And then that ionization is essentially a function of the energy loss in the TPC. So yes, in a sense, it does measure the energy loss if you understand a conversion of the energy loss into the number of electrons liberated. And then, because we're also measuring the trajectory, we know the dx over which that energy is lost. So we know the path length. And then with that information, you can do dN dx or dE dx. So these are things that the TPC can measure. So really, the TPC measures two main things, the position of the track going through, the particle going through, and it measures the ionization of the track going through. And those are the things that we can use for a lot of interesting physics. What does that mean that it doesn't, for example, measure the momentum directly? Well, what we do is calculate the transverse momentum from knowing the curvature of the trajectory. It's actually the radius of curvature of the trajectory, and knowing the B field. And then assuming that the magnitude of the charge is 1. Because if the magnitude of the charge is 2, for example, helium, which we do see, then you actually have to take that into account when determining what the true PT is. But the implication is that the TPC measures space points, and the errors that it has are errors on positions. These are not errors on the transverse momentum. So you want to think about how does an error on a space point translate into an error on momentum or PT. Well, PT is proportional to actually 1 over the curvature, and curvature is essentially determined by the space points. Curvature is a spatial metric. It's not a momentum metric. It's a space metric, a physical space. So because PT goes as 1 over the curvature, that means that an error in the PT actually goes as PT squared times whatever error there is in the curvature. So the resolution in PT goes as PT squared times the resolution of the curvature and the resolution of the space points themselves. And this shows up when you look at a plot like the one on the left here, which is of the momentum resolution versus PT. And this is a very old plot. Actually, it comes from the design reports 27 years ago or so, actually, with a few different possibilities overlaid. And I don't want to get into the different curves that are on the plot, but I want you to get the overall qualitative message that at high PT, essentially over 1 GeV, this is the dominant dependence for how the momentum resolution looks. You see this rise in PT for momentum resolution. In this case, momentum resolution would be delta PT over PT. So you take 1 PT out of the right side and you put it on the denominator on the left side. So delta PT over PT goes as PT. And so you see this linear rise at high PT. Now that would be true at all PT, except that at low PT, there is the increase of a different effect, which is multiple Coulomb scattering, which means that the trajectory that you measure at any given point or at any given portion of the track path does not necessarily reflect the actual momentum at the start of the trajectory. So the momentum that you get has some dispersion to it, some broadening of it from the fact that there was multiple Coulomb scattering. And this is an effect that rises at low PT. So at the very low PT, these curves rise up due to that effect. So that's exactly what we see. This is an old plot. There are more recent plots, but I don't want to spend much longer than this talking about it. But I want people to take out of this that this shape of the momentum resolution as a function of PT is a result of the fact that the TPC doesn't measure momentum. It measures the trajectory of the particles. It measures a spatial quantity, and this is the end result. All right, so I think probably many of the people here know how TPC works, but for anyone who possibly doesn't, just a quick recap that the charged particles, in the case of star, pass through a gas called P10, which is 90% argon and 10% methane. And it's not completely pure P10. There's some trace gases in there, and we'll come back to that a little bit later, but not too much. So as the charged particles pass through this gas, they ionize the molecules in the gas. And then these ionized electrons and the ions themselves will drift in a modest electric field. And the electric field is strong enough to cause this drift, but I want to be clear that the electric field is not strong enough to affect relativistic moving particles that came out of the collision. So this electric field doesn't bend the trajectory of the tracks that came out of the collision in the first place in any perceptible way. This is just much too low for that. But these comparatively slower electrons and ions do drift in this electric field, and it's designed so that the electrons drift to the end cap and the ions would drift to the central membrane, where they would then pick up electron and re-neutralize. So as they drift, they go through a magnetic field, and this magnetic field does two things for the TPC. The first is that, of course, it bends the trajectories of the original particles, which allows us to have a curvature that we can measure to determine the transverse momentum. And then, additionally, these drifting electrons, without the magnetic field, tend to disperse as they drift. They push each other apart, and they just wander as well. And the magnetic field tends to help reduce that effect, because as drifting like this is in the transverse direction at least, is then turned around because of the magnetic field, and the electrons, instead of just sort of wandering off, essentially take a helical trajectory, a spiral trajectory towards the end, and they stay much more narrowly focused as they get to the end. Then that means that the position that they arrive at the end cap is essentially more sharply resolved with respect to the position at which they started. And when they reach the end cap, there is a region of electrical wires that establish a high electric field. And these wires are arranged on hardware that we call sectors. So, for example, if you kind of look at this old picture in the top right, you can see these sectors are shown as 12 segments in azimuth and 2 segments in radii. So on each end, there are essentially 24 components to the sectors, and then 24 on each end plus 24 is 48 total segments like this. So there are the inner TPC sectors at the smaller radii, and there are the outer TPC sectors at the larger radii, and these are all numbered. We have maps of. Anyway, once the electrons enter this high electric field region near the end cap with the wires, that's where an avalanche is introduced in the gas of the TPC. So the individual electron comes in and can result in essentially 3,000 electrons that are a result of the avalanche. And those avalanche electrons all accumulate on high voltage anode wires there at the end. And then once that voltage accumulates, it is seen essentially by copper pads that are a little bit further out along the end cap, just a few millimeters beyond. These copper pads essentially develop a mirror charge to the charge that accumulated on the anode wires, and it's that mirror charge that is then read out, and it's pixelated. It's individual pads, essentially gives us an individual pixel of data, and how much charge gives us an amplitude. So the TPC gives us a full pixelated image, and we capture that pixelated image in 2 dimensions as a function of time to give us a 3rd dimension. So the full reconstruction of the 3-dimensional deposition of electrons at the end cap. All right, so way back 18 years ago, I found that I had dug up an old simulation that I did of this. So those of you looking at the PDF won't see this, but those of you who are looking at the keynote presentation that I'm showing will see it. And so the idea was to try to give people who are new to it some understanding of what this looks like. So on the left is a side view of the TPC, and the right is an end cap view of the TPC. And a brief blue picture is particles creating tracks, and then the green is the electrons that are a result of the ionization, and those electrons drifting to the end. And it takes about 40 microseconds for the electrons from the middle of the TPC to drift to the ends of the TPC. But it is the time at which they arrive at the end that creates this animated effect on the right, where the red dots are essentially showing you the reconstructed hit at the end cap as a function of time, and that time is then converted into depth into the TPC, the drift depth, so we get the full 3 dimensions. So just a little fun thing I had with writing a root macro 18 years ago and turning it into an animated GIF. So here's some actual pictures, most of these being from before the time of any of the juniors in the TPC. Back in the late 1990s when the TPC was actually installed in the star magnet. So if you've never seen this before, I think it's kind of neat to see the TPC outside the magnet and then getting inserted into the magnet in the star assembly hall in the top right, and a view from inside the magnet in the bottom left as the TPC slides in. So this is in the days before there was a TOF, and in this case, even there was no barrel calorimeter. So there wasn't much between the TPC and the magnet at that time. There were scintillator strips, what was called the central trigger barrel, a CTB. At the time, there were scintillator strips that were put outside the TPC, and that was pretty much all that was there. And then a few years later, the barrel calorimeter came in, and then several years after that, the barrel time of flight came in, and the barrel time of flight replaced the scintillator strips, the CTB. The bottom right picture is actually not from that long ago. This is a picture that I took of the ITPC installation work where the inner TPC sectors the old inner TPC sectors were removed and the new, more highly segmented and instrumented inner TPC sectors were put in. So behind that sector is a plastic-covered TPC, trying to keep as much dust as we could out of the inner volume of the TPC while those sectors were replaced. Anyway, just a little flavor of the actual hardware there of the TPC. So talking a little bit more about the details of the TPC operation, I already mentioned that the B field is critical to make the TPC do the job that we want it to do, to measure track momenta and to do it with good resolution. One of the things that we face is the fact that the B field is not perfectly uniform. The B field is provided by a series of many coils in the magnet which aren't completely perfect. And so the kind of essentially out close to the coils, you can see some imperfections in the B field. And the plot that I'm showing was a map of the B field taken before the TPC was inserted into the magnet. And the TPC doesn't occupy this whole volume in essentially radius and Z. The extent in Z of the TPC is only out to plus or minus 200. So the white regions you see are where there's actual hardware that from the magnet that interrupt the map. And then the TPC does start at a radius of about, well, the actual instrumented readout part of the TPC starts at about 60 centimeters in radius and goes out to about 190 centimeters. So particularly out there at the large radii, you can see there are non-uniformities in the magnetic field, and we just have to keep that as something to consider when we look at the performance of the TPC. The TPC itself defines its own electric field, and this is done through several features of the TPC. The primary high voltage of the TPC is provided by a single power supply that puts a voltage on the central membrane of the TPC, and I'll have pictures of the central membrane in just a moment. The electric field, then, we want to be as uniform as possible, going in straight lines from the central membrane to the end cap, and to help maintain that uniformity, the sides of the TPC are essentially what are called field cages. So the sides of the TPC are also the boundaries of the gas chamber of the TPC in our case. Doesn't necessarily have to be that way. For example, in Alice, the field cages that determine the potential going from the central membrane to the end cap are not part of the gas chamber walls. That field cage is actually a separate set of wires inside the gas volume. But in STAR's case, the field cage is the gas chamber wall. So the inner radius of the TPC and the outer radius of the TPC. And again, I'll have some pictures of this in a moment. But field cages then step the voltage down from the central membrane to the end caps at ground, essentially. So there are 4 field cages. They are all tied together at their high end at the central membrane, but the 4 field cages then take the current from the central membrane going down through 4 separate resistor chains. And between each resistor on the resistor chain, there is an electrical connection to a ring in the field cage that then is expressing the voltage, the potential into the TPC. So those 4 rings, of course, are the inner east, inner west, outer east, and outer west. So it's a very small electrical current that flows down these resistor chains. But if there's any modification of that current or any modification of the resistor chains, that will result in non-uniformities in the electric field. So something to keep in mind.
This is Joey Adams. Can I ask a couple questions?
Yeah.
First is, how does the uniformity of the electric field compare to that of the B field?
Let's see. The B field is smaller non-uniformity. I think it's a part in 1,000, essentially. Okay. And the electric field non-uniformities, for several of them, they're quite small, but for the space charge in particular, it dwarfs the magnetic field.
I see. So is this accounted for when doing track reconstruction?
Yep.
Okay.
Absolutely.
Great. Thank you.
Yeah, that's a big factor, is trying to understand any E-field distortions. I'll come back to that too. All right. At the end caps, you might think, well, the end cap is at ground, and that's kind of the way we say it simplified. But the truth is that the potential that's expressed inside the TPC doesn't come from the ground of the end cap. It comes from a grid of wires that is the innermost part of the end cap. And that grid of wires is called the gating grid, and it's essentially positioned not at ground, but at minus 115 volts. And then another plane of grid wires is behind that, or closer to the end caps, and that is at ground potential. And sometimes we call this the cathode plane of the TPC, but I'll come back to that in a second. But the potential that's expressed into the TPC isn't from that ground plane of wires. It is from the gating grid. And I'll come back again also to explaining why there's a gating grid in front of these ground wires. But the ground wires, we call it the cathode plane because it begins another region of the TPC, which I mentioned earlier. It's the high voltage, high electric field region where we want the avalanches to occur. So here, between that cathode plane and yet a third set of wires, which is our anode wires, there is a rather short distance and a high voltage of on the order of 1,000 or 1,300 volts over just a few millimeters, and this is keeping the high electric field. On the other side of the anode wires then is the ground plane. So I'll try to show a picture of this as well in just a moment. So here's some actual pictures of the hardware involved. At the top left is this central membrane in the middle of the TPC. You can actually, even if you look very carefully, I think you can kind of see through it a little bit in places. It's a really very thin Kapton sheet that's stretched out. And the middle picture actually shows that central membrane inside the TPC, where you can see a person. I often look at this and think, well, that person looks really small, but I think it was a wide-angle lens, so the person looks smaller than they really are. The distance from the inner field cage to the outer field cage is about 1.5 meters. So give you some sense of scale there. Then this kind of brownish orange cylinder that you see on the outside is the outer field cage. And if you look very carefully at that outer field cage, you can actually see the individual rings. And the bottom left picture is a close-up picture that I took when the ITPC sectors were being installed, where I looked down into the TPC at that outer field cage. So you can see those copper rings that step the voltage down through the TPC. And then also in the top middle picture, you can see the more silver-colored inner cylinder, which is, if I recall correctly, it's aluminum. I'm not quite 100% sure about that, but that on it you can see the rings that define the inner field cage. The bottom right picture shows a view down the inside of the inner field cage where you can see the resistor chain, and that resistor chain is actually not in the gas volume of the TPC, but you can see that some of the actual individual resistors there, I think, at the end. The top right picture shows this end cap region, and if you look very carefully at this, you will actually see the three separate planes of wires. At the topmost plane is the gating grid that would be inside the TPC, and then a few millimeters to the cathode plane or ground plane. And then I think you can only see one of the anode wires, and there are fewer anode wires than there are of the other planes of wires. So I think you can see just one anode wire and then the other planes. Additionally, you can see the pad plane that is underneath the anode wires with its individually segmented pads that do the readout. And those are essentially the pixels of the TPC. All right. Some people may not quite. Is there a question?
Yeah, this is Navjad. In the previous slide, where is the beam pipe? Is it inside this aluminum cylinder?
Yes, right. So the beam pipe is generally just a few centimeters in radius, and it passes through the center of that silver aluminum pipe that you see. Yeah. So there's actually quite a distance from the beam pipe to the inner radius of the TPC. And in many years, there's been nothing in that space. But from 2014 to 2016, we had the HFT hardware in that space. And in the 2006-2007 timeframe, we had silicon vertex tracker in that space. Also in that space, when a lot of people may be unaware that we had some additional forward tracking from, I think, 2003 to 2008-ish. And so the forward tracking kind of filled in at the ends of that tube, not in the middle of that tube. That was the forward time projection chambers that we had for a while in STAR.
And where is the P10 gas? Is it all around this between silver and that aluminum?
Yep. So where you see the person in that middle picture, that person is in the midst of the middle of the gas volume. So the gas essentially enters through a port on one corner, if you will, of the TPC and flows through the TPC and then out a port on the other side.
So gas is not inside this aluminum tube?
Nope, no. Inside the aluminum tube is open to air. So if you look in the bottom right picture, you can see essentially at the radii smaller than that tube, and that is just open to air. We tend to try to keep flow of somewhat fresh air going through that tube to keep it from getting hot and humid inside that tube.
Okay, thanks.
Mm-hmm. Yeah, good questions. I appreciate them.
Yes, I have one question. So, did you consider the distortion due to magnetic field, or it is just ignored?
No, we correct for it. We do correct for it. We assume that the map that was made of the magnetic field is correct. And the truth of the matter is that we cannot measure the magnetic field very well right now. We can't put probes all throughout that volume because the TPC is there, and so we can't measure it with the TPC in place directly. So the measurements were made before the TPC was put in of the non-uniformities, and that map is used to correct for the distortions due to that. Yes. Okay. All right. So I've thrown out the term gating grid a few times, and I want to help people understand what a gating grid is and why it's there for anybody who doesn't. So the drawing on the right is trying to show these three planes of wires in green, magenta, or pink, and red. And you can see that the green is the gating grid, the pink is the ground or cathode plane, and then the red is the anode wires, and there are fewer of the anode wires. And then the green horizontal stripes at the bottom reflect the pad plane on top of its supporting structure. And the reason why the picture is kind of separated into a left half and right half is because the outer TPC sectors are actually engineered slightly different from the inner TPC sectors. And the inner and outer TPC sectors are actually separate units of hardware that can be moved around independently. So the wires from one do not match right up to the wires of the other, and there's actually been a gap in those wires, and the new ITPC has a kind of a wall in this gap, and that's what I've pointed to there, but I'm not going to spend too much time talking about that wall at the moment. Later, if people have questions, we can come back to it. But the point is that you can see here what the planes of wires look like as viewed from the side in this drawing. So I've mentioned earlier that once the electrons that have been drifting reach the end cap, they go through this gating grid, and then they enter the high electric field region once they pass those cathode wires. And, this is great. It produces an avalanche with 3,000 electrons essentially coming in per incoming electron, which gives us a good gain so that we can clearly see the signal from the electrons that come in. The downside of this is that, of course, for all these electrons that we liberate in the avalanche, we also create about 3,000 ions. So the ions are not something that we want going back into the TPC, because those ions will essentially create a electric charge in the volume of the TPC, and that will cause an electric field that distorts the uniformity of the electric field that we want. So the gating grid is designed specifically to act as a shutter, something that can open and close to allow the incoming electrons and then prevent these ions from coming back out into the TPC. So I didn't include a picture of it here, but the closure of the gating grid is actually made to happen by taking alternating wires and raising their voltage or lowering their voltage by 75 volts. So because we do it on every other wire up and down from a distance, the gating grid doesn't look like it changes voltage when it opens and closes. The whole thing looks like it's at minus 115 volts unless you get up close to it. So when you're up close to it and it's open, all of the wires are at minus 115 volts. But when it's closed, one wire will be at minus 40 volts, and the next wire will be at minus 190 volts, and then minus 40 volts, and minus 190 volts. So this creates a transverse field that the ions coming out as they go slowly drift transversely, and instead of just passing straight through this grid, they curve and turn and then fall onto the anode wires that are at the more negative potential. So the positive ions drift to the negative 190 volt wires and then neutralize there. So that is essentially the way that the gating grid closes. As an additional help, when it closes, it also prevents electrons from passing through that are coming from the main drift volume. And this is valuable for a couple reasons. The electrons, as they ionize and create this avalanche, put a lot of charge onto the anode wire, which then is creating a current from the power supply that supplies the voltage to those anode wires. That current then sees some resistance and actually causes a dip in the voltage on the anode wires with respect to the voltage that's at the power supply. So you want to try to minimize this current and not create a sag in the voltage. Additionally, all of this charge that comes to the anode wires creates something called wire aging. And wire aging is a bit of a complicated topic. It essentially impurities in the gas of the TPC build up on that wire when large charges accumulate on the wires. So you get buildup of, I think the word we like to think of it as dirt on the wire, that are these impurities forming chemical compounds on the surface of the wire. They stick to the wire, and then because they are on the wire no longer expresses right there where that dirt is its full potential out into the gas around it. So the wire then doesn't perform. The electric field changes a little bit, and the gas amplification doesn't perform quite as well as you want. So it's a complicated thing, but you really want to try to prevent just piling tons and tons of electrons coming from the drift volume onto those wires if you can help it. All right. So hopefully I've given a flavor of what the gating grid is there for. I want to make special note in this time and age of a couple other experiments that use TPCs. The Alice TPC has had a wire grid at the end, like STAR has had, with a gating grid, but they've been going through an upgrade that will replace this wire region with GEMS. And the S-Phoenix TPC that's currently moving forward also, instead of having wires, will have GEMS. So GEMS also are designed to block the ions from going out, the ions that are created through the gain. They're designed to prevent those from going back out into the volume of the TPC. However, they aren't as completely blocking as gating grid wires. So, for example, you might get 1 in every 1,000 ions that are created still make it through. And then one has to determine whether that's an okay amount to allow through or not. This, of course, enables them to not have to open and close because the GEM operates in a continuous mode. You just stay at this potential and it blocks most of the ions, but not all of them. And because it's in a continuous mode, then you can just continually stream out data. You don't have to wait for this shutter to open to collect the electrons and see what happened inside the TPC. So it's a trade-off. All right. So I've already hinted the fact that the electric field can have imperfections, and those imperfections can arise in several different ways. And I want to emphasize that we've had it arise in all of these ways. So whatever can go wrong does go wrong. So I already mentioned that the field cages. Yeah, go ahead.
I have one question. So you mentioned that there's a gating grid,
Yep.
and then we have a MWPCY. Then there's also a shielding grid. What is the importance of shielding grid, and how it affects the field structure?
So you're talking about the cathode wire plane? Is that what you're asking about? The grounded cathode wire plane?
Yes.
Yeah, so that is defining the boundary of the high electric field region with the anode wires. So that is there to make sure that that region is independent of whatever is happening with the gating grid. So the gating grid we can modify, we can change the potentials, and that will have no impact on how the electrons go through the avalanche region, high electric field region where the avalanche going to the anode wires. So that region is kept independent of any other activity because it is essentially closed off in terms of the electric potential from what's happening out at the gating grid and beyond. Does that make sense? You feel like I've answered your question?
Yes, now it's
okay. Great. Yep. All right, so getting back to things that go wrong, the field cages can be misaligned. So, for example, this inner field cage could be shifted longitudinally along its axis, and we believe that it is by a couple millimeters. And that then, of course, means that the inner field cage isn't perfectly aligned with the outer field cage, and you get some slight tilt to the electric field. We can also have this resistor chain not be of proper resistance all the way along. And what has happened is that we have had instances where the resistors themselves have failed. We have also had instances where the material that's in the field cage between the rings may have become slightly conductive, in which case one ring to the next would have instead of an infinite resistance between it inside the TPC, you get a finite resistance, and that lowers the overall resistance between those two rings. What can also happen is that you could have conductive dirt in the gas of the TPC that could gravitationally fall onto two of the rings and possibly conduct electric current through the dirt from one ring to the next. So in any case, it's hard to know exactly what happens in all these cases because we don't get to go in and find exactly where the resistance has been lowered. We don't get to just open up the TPC and look around and dig for things all the time. So it's difficult to determine exactly what happens each time that the resistance changes, but we have had several instances where this has happened. And then another thing I'll bring up for the field cage is we've actually seen where it looks like electrical charges are deposited on the field cage rings. And of course, if you deposit an electric charge on the field cage, like let's say an ion comes to the field cage, it will draw an electron from the field cage, which draws that electron from the current that's flowing down the resistor chain. And once you draw electrons out of the current, you're changing the current over the resistors, and then you're changing the potential, and you're doing that part way down the chain of resistors. So a couple ways this can happen is that within the TPC volume itself, the ions that are drifting towards the central membrane push away from each other, and they can go out, get pushed out to the field cages as they push each other apart and then draw current out of the field cage that way. Instead of drawing current from the central membrane to neutralize, they draw current somewhere down the field cage. That can happen on the inside, and it can even also happen on the outside because the field cage rings are visible on both the inside and outside of the gas chamber. So, for example, air that's ionized inside that inner cylinder of the TPC, as charged particles come out of the collision, they ionize that air. That air, then those ions in that air can then go to the field cage and draw current from the field cage. And we can actually see that effect clearly. So again, that changes the potential partway down the field cage and then creates a non-uniformity. Then one other surface that I'll mention, of course, is the central membrane itself. Could be tilted or shifted towards one end or the other a little bit, and we believe we see a little bit of this as well. And that would, of course, create, for example, a shorter length over which the electric field is determined when it's tilted closer or farther from one of the end caps. So in addition to these surfaces, there is the volume of the TPC itself, where in the gas you could have electrical charges, or you can have the whole volume of the TPC not perfectly lining up with the axis of the magnet. Again, we've seen both of these things. So you could think of the TPC not lining up with the axis of the magnet as a misalignment, but it's not just a misalignment of the readout. Of course, it's a misalignment of the electric field, and that then creates a cross product between the electric field and magnetic field, which shows up as an issue. As far as electrical charges in the gas, there are two main sources of these electrical charges in the gas. The first is the primary ionization itself. Of course, as the electrons are liberated, you have ions, and those ions drift rather slowly. So I've mentioned that the electrons can drift in about 40 microseconds from the central membrane to the end cap. The ions drifting from the end cap to the central membrane take more than 1 second. So if you just have a very low number of collisions per second, a low rate of collisions, then these ions don't amount to much. They're not going to create much of an electric field before they are swept out to the central membrane. But if you have a very high rate of collisions, the ions from one collision build up and pile up on top of the ions from the next collision, and that piles up and piles up. And so you essentially have this high concentration of ions in the TPC. It's not a static concentration of ions. The ions are constantly drifting towards the central membrane, so there's a lot more of them at the central membrane than there are at the end cap. But you sort of get a steady state of the flow of these ions going towards the central membrane. And the ions then are all highly positively charged because of all the large number of ions. And then you get an electric field that has components that are transverse as well as longitudinal components. The longitudinal components aren't something we worry about too much. That doesn't really distort things, but the transverse components of the electric field are really the problem. So that's something we call space charge. It was expected from before anybody ever built the star TPC. It's been seen in the past. And the space charge that we see isn't considerably different than what one might have expected before the TPC was built. However, the TPC was built originally with the intent to operate it at a collision rate of 10 collisions per second or less. I think 8 was the number at the time. And if you're familiar with the way that we operate these days, we can operate with gold cold collisions anywhere from 50 to 100,000 collisions per second. So that's a huge difference from the original design of 8 collisions per second. And with the proton-proton collisions, we even can go up to 10 million collisions per second. So you get less charge out of a proton-proton collision, but the higher frequency of them actually makes the proton-proton collisions have even more space charge than we get with the gold-gold. So that's a big one, space charge. The one that wasn't expected was ions in the main volume of the TPC that came from the avalanche region. So I've already said that the gating grid is supposed to block these ions from getting out. And it turns out it does a great job of keeping them from getting out where there is a gating grid. However, I also earlier mentioned that between the inner TPC and outer TPC, there is a gap in the wires, because the wires don't just meet up right next to each other. And it turns out, we believe, that electrons are making it through this gap into the anode region even when the gating grid is closed, and ions are then taking the same path back out of that anode region into the main volume of the TPC even when the gating grid is closed. So the result is a nearly cylindrical sheet, if you will, of ions coming out of the avalanche region. So if you look, for example, at this picture in the top right of this page, you can kind of see this 12-sided cylinder almost that is between the inner and outer sectors. And so if you tried to connect that cylinder going across from the end cap to the central membrane, that's where this sheet of charge is flowing across through the volume of the TPC. And it turned out that this was significantly more charged than was expected. I have to say that there was design consideration for this. The last anode wire is a fat anode wire so that it has a lower electric field around it and a much smaller gain. So it was built to avoid this. But again, it appears that we had more gain than we were expected. And of course, we're operating at several orders of magnitude higher collision rate than we were expecting. So this added up to a lot of charge in this sheet going across the TPC, and that creates a distortion we call our grid leak distortion, because it's a leak of ions around the grid. So I want to emphasize it's not a leak of ions through the grid. They're finding their way around the edge of the grid. Yeah, go ahead.
Oh, sorry. So is the primary ionization, is it different from the avalanche ions?
Oh, yes. Yeah. So the primary ionization differs in two ways. Of course, it's happening all the time, regardless of anything that's happening at the end cap. So, you could have the anodes turned off and you wouldn't have any ionization at the end caps, but you would still be, as long as the particles traversing the TPC, you're going to get ions in the main volume of the TPC. And they are throughout the TPC. They're out throughout the entire volume of the TPC. Those ions then drift to the central membrane and pick up an electron from the central membrane. Essentially, a current from the power supply of the central membrane provides electrons to the central membrane, and that those electrons then neutralize the ions that have come to the central membrane.
But doesn't central membrane have higher voltage?
Yes, it's a negative voltage, so the ions drift there, and that's the direction they want to go, because they're positively charged. They drift to that negatively charged central membrane, and there they pick up an electron and neutralize.
Okay. But then the avalanche ions also go to the central membrane.
Yep, exactly. So the ones that get around the grid go to the central membrane. The ones that don't go around the grid, that actually get collected by the gating grid, they get neutralized at the gating grids. The ones that leak around the grid that are the problem here, they're getting out into the main volume of the TPC and drifting in nearly straight lines across to the central membrane.
I see. And can you remind me again where the gating grid is?
It's just a few millimeters from the end cap of the TPC. So if I go back here, the picture in the top right, the bottom of this is the end cap of the TPC. It's a little bit displaced for the inner and outer sectors. And the distance scales here are, I think, between the green and pink, for example, I think that's 4 millimeters. Is that right? No. It's the spacing between the wires is a millimeter. So maybe it is 4 millimeters. So this is just on the order of a few millimeters from the end cap. Okay. And then past that green, it's 200 centimeters beyond that green to the central membrane. All right. So all of these wire planes are within just a few millimeters. Here we go. So if you look at this top right picture, this is zoomed in pretty closely on these wires that are close to the end cap. And the spacing here between the wires is just a few millimeters. And then above this is 200 centimeters, 2 meters to the central membrane.
I see.
So
Thank you.
In that top right picture, you can see the gating grid wires, the topmost wires. Yep, good questions. All right, so the further complication that the grid leak number of ions that come out of that, of course, also depends on the voltage that you put on the anode wires. So there are parts of the TPC. So, for example, TPC sector 20 has been a problem for the last 20 years, essentially, because it cannot hold a voltage, the full anode voltage, on the anode wires that are close to the end of the outer sector there, close to this gap between the inner and outer. And because of that, it has a different grid leak distortion than all the other TPC sectors. So that's been sort of one of the problems for us for a long time. All right. I'm not going to spend a lot of time here on how we calculate the distortions. There are some documents on this, for example, the STAR TPC NIM paper, and there are been other presentations. What I do want to say is the distortions are, of course, calculable when you understand what the imperfections are in the magnetic field and the electric field. And then I further want to note that even a transverse electric field distortion can create a distortion in the electric field that is transverse, can create a radial distortion of the TPC hits. And similarly, a radial distortion of the field can cause a transverse. Yeah, goes back and forth is my point. So even if we have no azimuthal distortions of the electric field, if all the distortions of the electric field are in the radial direction, you will get a distortion of the TPC hits that is both radial and transverse. And the way to think of that is that the particles are moving in a magnetic field. So when the particles see, for example, a radial electric field, they start trying to go to lower or greater radius. And because they're doing that, the magnetic field makes them curve in their trajectory, in their transverse trajectory. So let's say the particle's going transversely towards larger radius, and then because of the magnetic field, it curves azimuthally as well. And so you get a distortion to the hits that's not just radial, it's azimuthal as well. And I want to emphasize that both of these distortions can have some impact, but the radial distortions are generally not as much of a big issue for us. They only really for low PT tracks do the radial distortions play a role. And to help people understand that, I've tried to make a couple schematics here that I kind of just did by hand, where the inner and outer cylinders of the TPC are shown, and then in dots are two tracks. On the left is a low PT track that curves a lot, and on the right is a high PT track that doesn't curve very much. And with these little arrows, I've tried to show the displacement, the radial displacement that one might get from electric field distortions. And you can see that radial displacement for a low PT track is going to twist the track that we reconstruct. When you look at the high PT track, the displacement is actually along the track itself when it's radial, because the track is radially oriented. And this means that a radial displacement doesn't have much effect actually on the shape, the physical shape that the track gets. And you don't actually see much impact from that. So the radial distortions are much more visible in the low PT tracks than they are the high PT tracks. But I also emphasized earlier that when we have distortions, the impact on the reconstructed transverse momentum goes generally as the transverse momentum squared. So even though we have the distortions on the low PT tracks, it tends to not be much of an issue for the reconstruction of the transverse momentum. When we look at the azimuthal distortions, pretty much all tracks get affected by these azimuthal distortions because of the generally radial nature of the tracks. So you can see the effects of the transverse or the azimuthal distortions more easily. And so this is really where we try to make sure we do things properly. We don't worry as much about getting the radial distortion as perfect, and we don't look for those radial distortions quite as keenly as we do for these azimuthal ones, because that's where we're sensitive.
So you're saying that the azimuthal distortions are not corrected for when doing track reconstruction?
Oh, absolutely. Absolutely, all of it.
Okay.
The radial and azimuthal, it's all corrected for.
Okay, great. Thanks.
Yep.
So maybe it's also worth explaining the specific choices for distortions that you choose, right? So that the electric field perturbation, so-called, is pointing outwards when it's close to inner TPC, and it's pointing inwards.
Why I did this one in particular, huh?
Yeah.
I did that because space charge is generally our largest distortion. That's not so true in the beam energy scan era, where we have very low luminosity, but in much of the other running of STAR, which we'll return to, for example, in 2022, space charge creates this large volume of ions. So the ions are positively charged, and if you were sitting at a given radius in the TPC, let's say you're kind of halfway between the inner field cage and the outer field cage, you'd see about as many ions outside of you as inside of you. And so the electric field that's due to that charge is actually minimum right in the middle of the TPC in terms of radius, when I say middle. While if you get out close to either the outer field cage or the inner field cage, here I'll show in the radial one, if you're close to the field cages themselves, you see all of that charge at a radius that's closer to the middle than where you are. So if you're at the inner field cage, you see all this positive charge outside of you. And if you're at the outer field cage, you see all this positive charge inside of you. So if you're a drifting electron, pretend you're a drifting electron, you're going to want to not just follow the primary drift field, you're going to want to also get pulled by this perturbation field, this perturbing electric field that's due to those ions there. And so the electrons are going to get pulled towards smaller radii at the outer field cage, and they're going to get pulled towards larger radii at the inner field cage. So they get pulled towards the middle as they drift. And that's why I selected the orientation of the arrows that I have here. Now, the direction of the azimuthal movement due to that is dependent on the magnetic field. So one magnetic field direction would turn you to the right, and one would turn you to the left, and I haven't put a particular direction for the magnetic field on this slide. So when I pick the azimuthal directions, whether it's left at the right, left at the outer radii and right at the inner radii versus the other way around is arbitrary. But that direction is opposite for the space charge for the same reason. So if it's getting pulled towards a smaller radius at the outer field cage, it's going to curve one direction. And that same magnetic field at a lower radius is going to curve the opposite direction. So in terms of, curving clockwise or counterclockwise, they're both at the inner radius or outer radius, they're both curving the same way clockwise or counterclockwise. But that motion, counterclockwise or clockwise, results in opposite directions azimuthally at the inner field cage versus the outer field cage. All right, a little complicated, but let me know if you got it. Good?
I have another question.
Yeah.
So the space charge come from the primary ionization. Do they move slower than the avalanche ions?
No, it's the same speed.
Okay.
But the avalanche ions, you start with that full sheet of charge at the end cap. All of that charge that's coming out drifts the entire way across the TPC. So you have just as much ions out at the end caps as you do at the central membrane. in that sheet of charge that's drifting across, while the primary ionization is deposited at all drift lengths, and it's drifting to the central membrane, so you actually get more of it at the central membrane once you've developed a steady state. So near the central membrane, you've got the integral of the ions that are created near the central membrane, along with ions that are created near the end caps, while for that primary space charge, the ions that are near the end caps are not the integral of what was created near the central membrane. So if you just kind of looked at the distribution of charge in terms of z, the longitudinal distance, the primary space charge is peaked near the central membrane, and that charge falls off as you go to the end caps. While for the grid-leak ions from the avalanche region, it's a flat distribution. There are just as many near the end cap as there are at the central membrane once you're in the steady state of ions just flowing across. Yeah, I appreciate these questions. I think you guys have some great questions. All right, so we've brought up the question a couple times, do we do anything about these field distortions? And I've spent a lot of time in this presentation on these distortions because that is what we spend a lot of time doing for trying to make the TPC work. And so the way we deal with this is we create distortion maps. So we have an understanding of the electrical charges and the electric potentials, and then we use that to essentially create an electric field distortion map and for each and every individual distortion. And then that distortion map can be used, you can integrate from over the drift distance to what the displacement would be at a specific location in the TPC for where it is reconstructed versus where it was actually produced. So you have an ionization, the TPC, instead of drifting to the end cap and you figuring out, okay, that's exactly where it came from, you drift to the end cap and you say, okay, I know how far into the TPC it came from and approximately where it came from, and I use that position to say, what was the displacement that put me in that position? And we actually do this a little bit carefully. You can imagine you don't measure the start position, you measure the end position after the distortion. So you want to be able to use the map to say, okay, what position would I have moved to get to this final position? Not what would this final position move to as another position. So we're careful about that. If you haven't followed me, then don't worry about that. But I do want to emphasize that we do create these maps, and an example is for a electrical short between two of the field cage rings that is shown here, where we know the potential differences that are caused by this, we know the electric field that's caused by this, and then we calculate a distortion map. And in this case, it was a sizable distortion of several centimeters. We do generally treat these as individual distortion maps that we can add one distortion on top of the other. And for the most part, the distortions are small enough that that's just fine. Really, with the space charge being the only one that's sizable, if we had two that were of that magnitude, then we would probably not want to do it perturbatively like this. We'd want to determine the electric field caused by the two distortions simultaneously and then figure out the distortion from those together. But for the most part, the distortions that we have are small, and doing it perturbatively like this is just fine. And, I've spent time actually trying to make sure that that's true, not just assuming it. A little bit of a side note on some other tools that we have for the TPC. We do have a laser system inside the TPC, and this is common these days for TPCs to use lasers. The lasers go through the gas of the TPC and create an ionization as well, and then you're able to look at the electrons and treat them as an actual track of a particle going through the TPC. So you can see these lasers, and if any of you have taken shift at the experiment, you know that every few hours we do run these lasers, and this has been a very, very useful tool for doing the drift velocities in the TPC. You should get the lasers at the same position every time, and so if you see them, for example, the distance between two lasers, if you see that change, then you can understand that as a change in the drift velocity in the TPC. And that's actually pretty important for us, so we do that. You can also imagine that the lasers form straight tracks. I mean, this is not, the laser itself doesn't curve in the magnetic field. So the idea has been tried many times to make sure that any deviations that we see from a straight track could be used to actually measure a electric field distortion, for example. And I have to say that for the most part, those attempts have failed And I bring this up as relevant because in the future, people are still relying on lasers, and relying on lasers has been great for the drift velocities, but it really hasn't been great for doing the distortion measurements. And the reason for this is that because the laser is always firing at the same physical location, when those electrons come to the end cap, they fall at the exact same place on the end cap. And there are systematics in the pads that are used to reconstruct these positions of the hits. The pads have their own imperfections, but further, the actual position of where the laser falls across a pad from one side of the pad to the other can lead to a slightly offset position of the reconstruction. So when you do laser after laser after laser, you might think, well, I'm gaining a huge amount of statistics. Sure, that's true, but you're gaining statistics at exactly the same place. It's not random statistics. And so whatever systematics there are in reconstructing the hit position, all you do is more clearly see those systematics. And so you, instead of being able to look for distortions due to electric field, you see the distortions that are due to these systematics. So that's just a word of caution that lasers are great, but they don't necessarily solve all problems. With that in mind, back in 2007, we started a different project to use gem chambers on the outside of the TPC to provide a high precision tracking point that we could then use as a measure of distortion. So for example, if you see that the projection of a track from the TPC to a point in this gem, if you see that projection have a displacement that changes with luminosity, then you can, for example, say, okay, we're not taking care of our luminosity-dependent distortions properly, like space charge. So it wasn't a huge project. There are only 8 of these gem chambers, and I think only 7 of them have worked, maybe 6 of them. So they're kind of scattered about in and they sit inside the TOF trays. So we took out 8 individual TOF modules out of thousands of TOF modules. So it wasn't a huge loss of TOF modules, but we took 8 of them out to put in these gem chambers. And we did that in 2012. And I'm very sad to say that this has been a project that no one has really picked up. So there have been a couple attempts to use it. And at least in 2017, it got to the point where somebody spent a good bit of time on aligning the gem chambers so we knew where they were. And there were some interesting results in that we could see, for example, different displacements in one orientation of the magnetic field versus the other. But the real reason this hasn't been picked up is because the software for reconstructing the gem hits is not in the main software stack for STAR. And that is because all software that comes in the STAR, that goes into the main software, goes through peer review, and nobody's ever taken it all the way through peer review. So I believe that once it gets through peer review, should that ever happen, that we'll make plenty of use of it. There's a lot we can do with it. We can do the drift velocities much better than the lasers. We can actually study distortions, like I said before. And I bring it up here because I would love to see somebody get excited about this and become invested in trying to make it happen. I think a lot of the few of us who made the effort to get the hardware in place have been a bit disappointed to see that the software hasn't come along for that. So, all right. I want to say that I'm not going to spend the time on everything. There's a lot more to get into, trying to understand the alignments. The alignment not only, of course, affects where you reconstruct the hits to get them in the right positions, but I've also mentioned that it impacts the electric field, and it can do that in a couple ways. The whole TPC can be tilted, so you get the electric field isn't aligned with the magnetic field. But you can also have, for example, if one TPC sector displaced longitudinally, then its gating grid is not at the right longitudinal position for that minus 115 volts. And so you actually can get a distortion of the electric field that way. A lot of time has been spent on alignment over the years, and I'm just not going to spend a lot more time on that here. Go ahead. The audio broke up a little bit for me.
When we have a gem. Hello?
Yeah, I'm really having trouble hearing your audio. You said that when we have gems, we don't have gaps. I will note that gems also have other things that I'm quite concerned about. So gems, for example, they have this backflow of ions that come through them. that flow of ions can be possibly varying with time, as the gem performance may fluctuate with time, and it can also vary with position on the gem. So one region of the gem may have a larger backflow of ions than another one. So understanding that backflow of ions is a very complicated thing for the gems. And so I wish S-Phoenix and Elise good luck with doing this. I'm quite intimidated by the prospect of trying to understand that backflow of ions and do the distortion corrections for those ions that have a lot of variance. Go ahead. If I'm picking up the pieces of what you're saying well enough, one of the downsides that we have with the gating grid is that it takes a moment to open the gating grid after an event is triggered. So during that short bit of time, the gating grid is not fully open. So the first few electrons that drift to the end don't come through the gating grid because it's closed. So you're inefficient to hits in the TPC that are actually deposited from the triggered event near the end caps of the TPC. So you have a low efficiency there. But then after it's just a few microseconds, the gating grid then becomes fully open and is efficient for all drifting electrons after that. But I'm not sure if that's what you're saying, but trying to pick up the pieces of the words that I did here. Okay. All right, moving on. I also haven't spent much time on the drift velocity. The drift velocity has its own set of complications. You have to take care of trying to keep the gas contents uniform in the TPC, and I don't just mean the argon and methane. Like I said before, there are trace gases in the TPC, and these change the drift velocity, and we do keep track of the drift velocity not just for reconstructing the positions of the hits in terms of converting their drift into their position. The drift velocity is also a factor in calculating the distortions. So we use that drift velocity in the calculations. You can see that if you go look at the calculations for the distortions. I've also not spent much time on the other grand thing that the TPC can do, which is doing particle identification through the energy loss in the TPC. And this is an area that could have plenty of treatment on its own, but I'm just not spending time on it today. Again, that has a lot of dependencies. What trace gases are in the gas, voltage on the anodes, which aren't all at uniform voltages. And it's not just a matter of counting the number of electrons that make it to the end cap right. When you do DEDX, you also need to get DX right. And when a track is distorted, that means that the path length that you measure at the end cap isn't necessarily the same as the path length that created those electrons in the first place, because the track essentially has distorted as it drifted for the electrons from where it was created to the end cap. So a lot of complications there. I'm not going to spend a lot of time on it. DEDX is another area that deserves a lot of attention on its own. So, you've heard me talk about a lot of things that can go wrong in the TPC, and a lot of it is stuff that comes up as a new thing for us to deal with pretty much each and every year. And so the TPC has always demanded a lot of attention from us to try to figure out anything new that we see each year. The space charge and grid leak were things that we saw early on as we ramped up to luminosities beyond what the original design was. Field cage electrical shorts we weren't expecting, and to complicate things there, sometimes those field cage shorts aren't constant. We see something kind of like a sparking between field cage rings. And so correcting the distortion for it means keeping track of how the electrical current changes with time. And that was a new complication. And I have to say, those haven't gone away. Even here in run 20, we're still seeing time varying field cage shorts on one of the field cages. We had difficulties with doing the alignment in run 7 towards run 8, and then we realized that still wasn't right and came back to it between runs 10 and 12, and we had to do alignment again now with the ITPC here before runs 19 and 20. We had to deal with the fact that when we have asymmetric colliding systems, we have different deposition of ions in the TPC on one half versus the other, so that leads to an asymmetry in space charge. We saw places where the gating grid wires weren't all at the right voltage, and so we actually do have ions leaking through the gating grid at places where gating grid wires were floating. We've had the fortune to be able to actually set it so that the floating wire is not the minus 190 volt wire, but the minus 40 volt wire when it's closed. And that's closed up those holes for the most part. What else? Well, I mentioned some of these I've already talked about. In more recent years, we've had issues with the way that the collider operates that have led to background tracks in the TPC that aren't from collisions. So I bring this up with the terms of port gap cleaning and booster main magnet. These have caused us distortions in the TPC that aren't strictly from the collisions that we want, and that complicates the correction of those distortions. So let me just finish by highlighting a couple of those recent topics. First I'll mention is the booster main magnet, and I bring this up because this is now an issue even here in Run 20 that I'm trying to look at and understand better. And you may hear about this if you're on shift and working at the experiment. So this is an example of a run taken just in March, just towards the end of our running. And on the left are some plots that are provided by the collider folks, and they're showing the various things as a function of time. And in the middle plot, you can see the beam intensity in each ring. So the yellow ring comes up, and then once they've got the yellow ring full, then they bring up the blue ring. And so they're filling the rings. And when they're filling the rings of RIC, they have to operate the other accelerators in the complex. So the RIC is fed by an accelerator called the AGS, and the AGS is fed by another smaller accelerator called the booster. And so the booster, as it operates for this period of injecting beams into the AGS and then into RIC, that the main magnet of the booster is turning on and off to essentially circulate the beams and dump them out towards the AGS. And one might think, okay, this isn't something related to STAR so much. We're at RIC, and the booster main magnet operates at a facility that's hundreds of meters away, and you're not going to see any impact of this. Well, it turns out that when they use the booster main magnet, they pipe huge amounts of electricity into and out of the magnet, and it's really on a large scale. And some of the people who operate the machines tell me that when they're at home, tens of miles away from the lab, they can actually see their lights flicker when the booster main magnet is operating. So it has an impact on the grid, the electrical grid as a whole. I can't say I've seen my lights fluctuate, but then I don't know exactly all the times. However, because it's impacting the power grid, it actually then impacts the performance of the magnets in RIC, which are on the same power grid. So the magnets at RIC just have a very, very tiny fluctuation when the booster main magnet is operating. And this tiny fluctuation then causes fluctuations in what the beam's doing. And the beam may move slightly from one side to another as the fluctuation occurs, and it may scrape collimators that try to keep the beam, in the center. So if your beam is slightly shifting a little bit into the collimator, you're going to get backgrounds from the beam scraping the collimator. And then those backgrounds can go into the STAR TPC and causes distortions. And this appears to be what we see. So in this particular example, in this run, the pink vertical line on the left plots is the time at which the collider folks declared physics. They said, we're done with injecting beams. You can go ahead and start collecting data. So at STAR, particularly during the beam energy scan, we're eager to collect as much data as we can. So what people do with the experiment is they start a run with 0 events. And so the run goes into a pause, but you get through all the overhead of starting the run. And then when the collider folks declare that it's time for physics, the person who's operating the data acquisition at STAR triggers it to start with a much larger number of events. So then you don't have the overhead of starting the run. You immediately begin taking events right after the collider folks declare physics. Well, it turns out that even though they've finished injecting all the beams into RIC, they don't instantly turn off the booster main magnet. It goes for another half minute or something like this. So what I'm seeing in the Run 20 data is that operation of the booster main magnet is affecting our TPC performance for those extra seconds. So the plots on the right are a zoom in of this booster main magnet on the top, the currents from that. Tried to align these in time, and you can see this is just a plot over 40 seconds at the beginning of the run. And in the red on the bottom plot is a metric of the distortions in the TPC. And you can see that those distortions come perfectly well aligned with the operation of the booster main magnet. So two completely independent sources of information. The booster and main magnet currents that I'm getting are in a database for the collider people, and the red is from the data that we have acquired in STAR. And these two things are directly correlated. So it's like when people say they see the tides or the passing of trains having an impact on their experimental data. We see an impact from the operation of this booster main magnet. I also show that we see an impact from the booster main magnet in our scalars. So we keep track of backgrounds at STAR by scalars. However, the scalars that we keep, we've really never tried to worry about getting them precisely timed to within 1 second of what's happening. And here in this case, these fluctuations are happening on the 1 second time scale. And our scalars are delayed by something close to 3 seconds for what goes into the data. So right now, the data that we have, the scalars don't match in time what's happening in terms of the distortion. And that will make it essentially impossible to correct without a lot more work. So it's just a few seconds of data at the beginning of many of the runs, and what we'll probably do is actually discard that data. So if you're at the experiment and you're collecting data and you see the scalars, you may see this effect. All right, another recent topic in the news that I'll bring up is something we've tried to deal with the fixed target running that we didn't really think about before we started doing the fixed targets, and that is that the beam bunches are pretty long for these low energy beams that we're bringing in. And that means that when the collision happens, the collision could be due to particles anywhere within that beam bunch. And being anywhere within the beam bunch spatially also means that there's a significant variation in time when the start of the bunch passes that fixed target versus when the end of that bunch passes the fixed target. So that's a time of maybe 10 nanoseconds, like that. But that's enough time to actually cause some drift in the TPC. So we're actually seeing that the TPC, if we don't account for this displacement in time, we see a displacement in the reconstruction of hits inside the TPC. And the plot at right is just to try to show a way that we observe this, and we're trying to correct for it. Essentially, what we're doing in this plot is we're getting time on the horizontal axis by grabbing that time from the first time that something gets hit in the EPD. So that gives us a reasonable metric of the time. And then the vertical axis is where we reconstruct a primary vertex from all the tracks in one half of the TPC versus all the tracks in the other half of the TPC. And those two vertices will get displaced if we've misinterpreted a time difference from when the collision happened as a time of drift. So this is showing that nice linear correlation. That's something that we can subtract out. So this hasn't been a very complicated thing to do, but it has been a new thing, and I just thought I'd mention it so people hear about T0s in the TPC for fixed target. That's been what that's about. All right, so that's bringing me to my summary. It's been 20 years of operating, and I've said there's been a lot of difficulties, but a lot of effort has gone on to make it work, and it's operating far in excess of its original design requirements and still doing quite well. And now with the ITPC upgrade, looking forward to even seeing better data here in the BES2. I think if people are interested, there's always work to do, but it's not typically work that you just go in and turn a crank. So when people get involved in the TPC and helping us do the calibrations, there's not often a need for someone to just come in and do something for a few weeks. You really need to kind of get some expertise in what it is you're trying to help with, and that can take a long time. Also, I say this with respect to the fact that each year we get some new issue that we didn't realize we're going to have to spend some time correcting. Each year we say, okay, next year there won't be any issues, right? But then each year there are, and then we say that again for the next year. So I think it's not realistic to think that you get high quality calibrations out of TPC right on day one. Just, it never happens. And so experiments that talk about throwing away TPC hits in favor of just keeping TPC tracks online so that you don't keep the hits offline, I think that's going to be a challenge, and good luck to the people who try to do that. maybe it'll succeed. I'm not saying that they won't, but I think that's a really tough challenge. I think even with all the work we've done, there's still room for improvements on doing the calibrations. We're going to have a lot of space charge again after BES2 ends. And so coming back to trying to improve that's going to be, I think, perhaps the topic of the day when we get back to the high luminosity running. And I think if somebody got involved in the GMT, that would be a place where it could have a high impact. I put a couple links to more materials that people can go to if they want, but that concludes what I wanted to say. Thanks.
Thank you. So before we go into the comments and questions section, let's thank Gene, so virtually clapping, for providing us such a great introduction to this big and very important topic. Thank you everyone who joined us today, and let's take a few questions if anybody has them.
Can I ask you a question?
Hello.
Hi, this is Navjan.
Yeah,
Yes,
go
we
ahead.
can hear you.
Okay. I don't know, is it the right place to ask about this thing? I have been hearing about the Sector 20 issue, and how long has it been there, and what effect does it make for our data taking or for our PIDs?
Yeah, you can ask. And I know Dimitri, as the moderator, has also probably had to deal with the Sector 20 issue many times himself, so it's worth talking about. So I tried to bring this up earlier, and maybe it got lost a little bit, but the TPC Sector 20 has a group of anode wires that have generally not been able to hold full voltage. And if those anode wires were in the middle of the sector, that probably wouldn't have been an issue for us ever. They essentially don't get hits there because the anode wires aren't holding voltage. But the real issue is that those anode wires that are not holding voltage are right at the edge of the outer TPC sector where it meets the inner TPC sector. And that is a region where the grid leak distortion that's created by ions coming out of the anode region are impacted by that. So the ions that come out there is a significantly different amount of ions than for all the other TPC sectors. And that leads to a distortion that is no longer as mutually symmetric. And getting that irregularity of the distortion there properly corrected is something that we didn't focus on a lot for a long time. We just sort of swept it under the rug for a little while, and then when it became a bigger issue, instead of trying to deal with it, a lot of times we just asked people not to analyze tracks that were going through there. And then a few years ago, I did try to modify the distortion maps to better account for what's happening in TPC Sector 20. So for example, the current Run 17 reproduction that we're doing right now, the main thing that we're trying to get better, more properly calibrated is exactly that. So I'll be excited to see whether the physics results out of Sector 20 are going to be usable or not. I know that without that improved calibration, they're definitely not, and I'm just hopeful that we've got it to a good enough place where it can be used for physics.
Okay, and how long has it been?
Day one, essentially. There was one, and maybe it was during BES1, like 2012 or something like that. The luminosity was low enough that somehow the anodes managed to hold their voltage there. And for a little bit of the running, we had that anode at full voltage. So it wasn't a problem. But for almost all the data since day one, that Sector 20 has been an issue.
Okay, thanks.
Yeah.
So we had another question I heard. Okay, in that case, I had another question about Sector 20.
Oh, great.
So,
see, I knew you
or
had.
maybe specifically grid leak. If the grid leak, you say, creates the trace of ions cutting the TPC between inner TPC and outer TPC, in that case, wouldn't we be able to quantify it if we were looking at halves of the track, right? The track in the inner TPC and the outer TPC, and try to see how well they match?
Yeah, that's essentially what we do. We haven't focused on getting that perfectly right for that sector. And the calibration that we're doing now hopefully gets that more accurate. But
And
that's
so-
exactly what we do. What we do is we take tracks that connect across from the inner and outer. We don't try to reconstruct two independent tracks and try to match them up. One could try to do that. That's a little bit tough. But what we do is we try to get the grid leak distortion corrected at least well enough that we're connecting a track across the inner to the outer. And then we're looking at how much the reconstructed hits are displaced from that track. And we try to correct the distortion to the point to where those hits on the one side on the inner sector are not displaced differently from the hits on the outer sector, so that they all line up along the track again.
Great, thank you. So maybe any other questions? I don't hear any, so we thank Jin again.
Sure. Yeah, thanks for having me, guys. I appreciate all the good questions.